Guys, welcome to my YouTube channel. I just promised you to do more examples on limiting reactant equations, and for the limiting reactant, instead of just a simple line of going from one substance to another substance, we had to actually form a table. Okay, and that table was crucial in solving the limiting or in addressing the limiting reactant problems. That's what today I want to address, actually solve more cases, two more cases of limiting reactants, and then once I do so, I actually answer every component or every possible question that you might encounter, not just the question that the problem itself is asking. Let's go for this reaction: chromium 2O3 plus Si, giving you chromium and SiO2. The balanced form is 2, 3, 4, 3, and the molar masses are 152.0, 28.1, 52, and 60.1 for SiO2. And the problem is asking if 350 grams of this is added to 235 grams of silicium, and it produces 230.2 grams of chromium, then what is the percent yield for chromium? So you have to go to the table, find out the theoretical amount, that is maximum amount possible for chromium, and then divide that number with the theoretical yield for chromium to get the percent yield. That's the biggest strategy. But the first step in these kind of problems is to start with two reactants, which is these two, and convert them to moles and then form the table. We ignore any products at this stage because this is the actual yield, and then at the end of the problem we will go back to this to actually use the actual yield. Once you have the theoretical yield, we can divide the actual by the theoretical to get the percent yield. So 350 divided by 152 would gives you mole of chromium oxide. 235 divided by 28.1 gives you mole of silicium. The mole of silicium would be 8.363, and the mole for that is 2.303. Okay, and then you form your table. The most important thing on the table is the reference line. So the coefficients come into play. 2, 3, 4, 3. This is SiO2, this is chromium, this is silicium, this is chromium oxide. So that's the reference line. I'm also interested to do columns here to make sure that I have enough columns. And I put the available amount of my chromium oxide here below chromium oxide, 2.303. That's the available, so I circle it. On a separate line, on a separate row below, I would put the other component, the other reactant that I have, 8.363. That's also the available amount, so I circle that, and I then go to the ratio table thing to address the blank ones that I have. Okay, I'll just use that to complete my table. So in order to do that, I just ignore this and say the diagonal divided by this to get this blank. So this times 3 divided by 2, that would give me 3.455. This much is the amount that I need. I have 8.363, so I subtract, and this is going to be excess because I have more available. And if I take this subtracted by that, it would give me 4.908 moles of excess silicium. If now ignore this one and compute that based on the two reference numbers, I have the diagonal again, 2 times 8 divided by 3, and that would be 5.575. And I do know that I only have 2 moles, or 2.303 moles. So this would be the excess, and I would have an up zero amount of that. This is the limiting reactant. Okay, sorry if I told excess. This is limiting reactant. I would actually have zero amount of it because I need this much, and all of the two is going to be consumed. So again, the most important step here was to recognize which row do we continue for the products. Okay, so we go with the limiting reactant column. This is the column of the limiting reactant, and with the row in this limiting reactant column that have the available amount. So that is this row, first row, and I use that to go on to the other side. Again, I want to compute this and this. For this, I use either this one or this one, no matter which one you use. If you use this one, that would be 3 times 4 divided by 3. If you use that one, that would be 2 times 4 divided by 2. Any one you do, and you will find 4.606. For this one, I just used to work with this because they have the same number, and that saves me doing any calculation. 3.455 times 3 divided by 3 would be itself. Okay, so I could compute how much gram of SiO2, how much gram of chromium is going to be used. First, let's address the problem's interest, which is the percent yield. If this much of chromium is produced, let's see how much chromium is going to be maximally produced, the theoretical yield for that, and let's put it in red here. So this 4.6 times the 52, that would give us my bad, let's see, 239, I believe, 239.5 gram of chromium would be produced. For that one, SiO2, you just take this number times that, and that gives you 207.6 gram of that would be produced. How much of the excess would be, you would end up having, how much of silicium excess? This would be 4.9 times that, and that would be just 137.9 gram of excess silicium. Okay, and for the sake of doing the problem's interest, let me just get rid of the first part of the solution here and use the opened up space to put the percent yield. Okay, so the amount of the maximum, the theoretical yield for chromium is this, and that much is what is the actual. So the actual is that divided by the theoretical, 30.5 times 100, and that should give you, let me just use another color, that should give you 89.02%. Okay, that's the percent yield of the reaction. Okay, so this is the whole bunch of information that we could get. We could find out how many grams of this, and this would be produced. For the limiting reactant, it's of course 0. For all the others, you have to get that mole amount and multiply by the corresponding molar mass. And if you have a problem that actually gives you the actual yield for any other two products, you could actually get the theoretical yield and compute the percent yield as well. Let's move on to yet another example, because we still have enough time to do one more of these problems, and then I would wish to wrap up this video as well, and we should feel okay and fine with any limiting reactant problem. Let's say we have a problem like P4, this beautiful molecule that I've been waiting for, the P4 plus Cl2, the chlorine I don't have a model of, giving you PCl3. The balanced form is just 1 P4, 6 Cl2, and 4 PCl3. That's the balanced form. And the molar masses are, by the way, 124. This is what we started with when we talked about the molar mass the first time. 71 and 137.5. Okay, there we go. Now the problem tells you if you use 20.5 grams of that and also 20.5 gram of chlorine, how much of PCl3 would be produced, which one is a limiting reactant, and how many grams of excess is actually left. So we have to do a table and address all those three questions for this problem. This is my favorite problem because it actually asks about every information, every bit of information that you could actually extract from this problem. Again, the first step is to actually convert the amount of grams to moles, and moles is the appropriate form that we could actually produce a table with. Okay, so 20.5 gram divided by 124, that's moles of P4, and 20.5 gram divided by 71, that's the moles of Cl2. Okay, and with that we could produce a table. So this would give me 1.65, and this would give me 2.89, and I could go on and produce a table. Now the reference line is, if you have nothing, it's just 1. Let me just put it a little bit down here so I could use that. 1, 6, 4. This is P4, this is Cl2, this is PCl3. We just have, okay, that's it. Now I would insert the amount of moles for my phosphorus here, 0.165, circled, that's my available, and for my Cl2, 2.89, also I circled that because that's also my available amount, and there are in different separate rows. Okay, so to find out this, I would ignore that one and I would just go to my reference line. This means the diagonal, the noun diagonal, I have a 1 and I have a number, so 1 times that number divided by 6, that gives me 0.048. I need 0.48 or I need 48 and I have 165. Okay, so if I take this, so this is going to be my excess because I have more, and if I took this minus this, that would give me 0.117. That's the amount of moles of phosphorus excess, and this one you could almost instantly understand that this is going to be your limiting reactant, but then you have to compute this. Let's do that. So this would be the known amounts, diagonal, the noun diagonal, this times 6 divided by 1, which would be itself, and that would be 0.998. Let's just write it in a smaller fashion so that we could have all of it, 998. So that's this, and I only have 0.28, so you could understand that this is going to be the limiting reactant, or you would have 0 grams of it at the very end, at the very last. Now this is the limiting reactant column. We go with the row that has the available amount in it, and that would be this row up here, down here. So I would have to ignore the one on the top. If I do ignore that, I could go on and compute this final product that I have 4. You could either use this one times 4 or use this one times 4 divided by 6. Okay, anytime you any one you do, you will end up having the same number, and that number is 0.192. And to find out how much of product I could get, I should just take this mole, multiply it by the molar mass to get the grams, and that would be 26.4 grams of, my bad, 26.4 grams of PCl3 would be produced Also for this one, I know that is 0 gram because that's the limiting reactant. For this one, I have this much mole times the molar mass for P4, and if I do that, I would find that there would be 14.5 gram of excess phosphorus. So 14.5 gram of your phosphorus, the P4 molecule, would be left over. That means you're not going to consume it. I think if you follow all the problems that I have done here on the limiting reactant problem, you would have realized so far that making a table is important. To make a table, you need the amount of grams that is given converted to moles first, and whatever you read off the table is not going to be the final answer. Those are the amounts in moles, so you have to multiply them back by the molar mass to get the grams that I just did. It's easy, it's just a little bit of practice and a little bit of passion with the chemistry to make you actually handle any question on limiting reactant. I think that's this, and I want to wrap it up here for this video.